to develop such a theory. So let me just start with some definitions. So suppose we have a quadruple sigma, alpha, beta, and w, and we say that it's a multipointed Heegaard diagram if the following happens. So first of all, sigma should be a closed oriented surface. So it's a genus G surface. I don't think I will use this fact, or the genus ever.
I think you should explain the notation.
So that's what I'm doing now. So sigma is a closed oriented surface. And we do one step at a time. So now we turn. Alpha is a collection of curves. K curves, alpha I, simple closed curves. And we assume that they are all disjoint. And there is a homological assumption, namely the dimension of the subset spanned by the homology classes represented by these curves, alpha I goes from 1 to k, should be of dimension G. So it's a genus G surface, so the first homology, so these are all elements in the first homology of sigma. It's a 2G dimensional free abelian group, and the alphas should span half the dimension, and similarly for the betas with the same properties. And so the two numbers should be the same. So the curves in the system alpha should be the same number of curves as the curves in the system beta, and they should intersect each other transversely. And finally, there is an assumption for the W's. And the last one is that every component of sigma minus alpha, by which I just mean that we delete all the alpha curves, contains a unique element of W, which is just a collection of points. So let me just spell out this last assumption. So sigma is a surface, alphas and betas are collections of curves, and the W is a collection of finite linear points in the complement of the alphas and the betas, such that every component of sigma minus alpha contains a single point, and likewise every component of sigma minus beta contains a single point. Also, every component of sigma minus beta contains a single Wi. Okay, so in fact this condition determines somehow how many W's we have. Notice that the traditional definition of Heegaard-Floer homology involves exactly G alpha and G beta curves, and in this case we need a single point to place somewhere. But this is sort of a slightly more general notion, and that's the explanation of this adjective multi. So it's a multi-pointed Heegaard diagram. Okay, so let me just give you one example, a very simple-minded example. So the surface will be the torus, and we use the usual convention of picturing the torus by a rectangle with sides identified. And then I put n alpha curves, and n beta curves. And I have to assign a rule for placing the w's. Remember that every component should contain a single w. What are the components here? These are these annuli, because when we glue up the top and the bottom, then this column will just glue up to an annulus, and it reduces to a chess problem. You have to view this as a chessboard, and then we have to put down rooks such that no two rooks are in the same column or in the same row. So for example, this is a good way of putting down, right? And this one will be identified with that domain. Does that make sense? And of course there are many other ways to put the w's. So these are the w's, sorry. W1, W2, W3, W4, and so on.
Is that K cube element of W?
Say it again. K minus G.
Yeah, K minus. So K, what is K?
Well, K is how many alphas we have.
Oh,
That's a K.
Oh, I thought.
So not n.
Oh, yeah, well, you know. Where is n? Okay. There are these equivalence relations between various letters, but yeah, this is K now. And then, of course, in this case, K is just 4.
If K equals to G, just reduce the original.
Say it again.
If K equals to G, then the
K equals to G, then that's sort of the traditional setup, but it will be more convenient to work with these slightly more general diagrams. Okay, so here is a fact. A multi-punctured Heegaard diagram determines a three-manifold. And the way to see it, well, it will be much easier to see after David tells you this, or tells his story about handle decomposition of manifolds, especially in low dimension. But let me just draw a little diagram for that. So this is sigma, and I crossed it with the interval 0, 1. So this whole thing, I hope it's sort of visible. This is sigma cross the interval, a three-manifold, and and I copy my alpha and the beta curves. The alpha's down here. Let's say this one, and the beta's up there. And now what I will do is I will just glue three-dimensional two handles to this product along the curves. So what you have to do is you just take these cupolas. You see these are sort of thick discs, and you just glue them along these circles on the top and from the bottom. And what happens is that in this way we build up a manifold which will have a couple of S2 boundaries, and then we just close them up with disks. So this is a way to get a three-manifold out of a multi-pointed Heegaard diagram. And what we would like to do is, once a multi-pointed Heegaard diagram is given, we would like to produce a Floer theory, and hopefully for different presentations of the same three-manifold we would like to have the same Floer homologies. Of course, in order to do that, we have to understand what different multi-pointed Heegaard diagrams produce the same three-manifold. And here is the first statement.
These points, these multipoints do not play a role.
Not yet. Actually, they do play a role because they correspond to these maxima and minima, but they will play a significant role in the definition of the boundary map in the Floer homology, but not in the construction of the three-manifold. Okay, so now I will list 4 moves we can do with these Heegaard diagrams. Isotopy. So that, let's call it 1. It's just isotope the alpha or the beta curves by still respecting the properties. So at the end of the isotopy, they still have to be transverse to each other, and they have to respect the position of the points. The second is Handel slide, which looks, I will just draw a diagram. So if we have 2 curves of the same type, 2 beta curves, 2 different beta curves, beta 1 and beta 2, then we can slide one over the other, which just means that we just take a nearby copy of the second one and connect some with the first. And this will now be beta 1 prime. So if we have 2 curves, we make 2 new curves out of that. One of them will stay the same, and the first one will be sort of the connected sum of the 2. Okay?
For isotopy, did you say just at the end it's satisfied, or all for all time?
Well, you can't do that, right? I mean, the transversality is lost. So,
okay, so you can do this. You can do like right dimension 2 type moves.
Yeah. So not among the alphas. So the alphas, they always stay disjoint from each other. But what you can do is there is something like that, and then you can turn it like this. So that's an isotopy.
They can push across the W's somehow.
No, the W's they always have to stay in the different domains. So they have to respect the W. So if there is a point here, then you cannot, that's not an allowed isotopy. Okay, and then there are 2 more. There is a type G stabilization. Here the G stands for the genus, which just means that we have a sigma alpha beta W, and we connect sum it with T2 alpha 1 beta 1. So by connect summing, I mean that we take the connected sum of the 2 surfaces, and in the T2 factor, I just take one of these alpha and one of these beta. So I don't change the number of base points, I increase the genus, and I also increase the number of alpha and beta curves. And finally, there is a type B stabilization, where I don't touch the genus, but I will increase the number of base points, namely in one domain. So I will just draw. Something like this. I just put 2 new curves, an alpha and a beta, and I put the W in here. So of course you can formalize it by saying that you have to pick 2 disks in a component of sigma minus alpha minus beta, such that the boundary curves intersect each other exactly in 2 points, and you put a base point in the intersection of the disks. Okay? So the fact is that that sigma 1, alpha 1, beta 1, W1, and sigma 2, alpha 2, beta 2, W2 produce diffeomorphic three manifolds if and only if sigma 1, let's call it D1 as Heegaard diagram 1, and this is D2. D1 can be transformed to D2 using 1 to 4 and the inverses. So we have 4 moves, and we can perform their inverses, and with a finite sequence of these moves we should be able to go from D1 to D2 if and only if the associated 3 manifolds to these diagrams happen to be diffeomorphic. Okay, so instead of 3 manifolds, I will always consider these Heegaard diagrams, so a surface, couple of curves, and couple of points. So here is how we associate to it the homology groups. So I just give you a recipe which associates to such an object a chain complex by the following way. So consider the k-fold symmetric power of sigma, equip it with a symplectic structure, and take T alpha and T beta to be the product of the alpha and the beta curves. So there are a few remarks in place. Typically, so what is the symmetric power? Well, we just take k copies of sigma and we take the direct product. This depends on somehow, this corresponds to the set of all ordered k-tuples of points of sigma, and we just factor out with the symmetric group on k letters. So the points in this vector space correspond to the unordered k-tuples of points of sigma. The group action is obviously non-free, so typically such a vector space is not a manifold, except if you start with a two-dimensional manifold like we do with sigma. Then because of some miracle, which is typically called the fundamental theorem of algebra, this vector space turns out to be a manifold, a smooth manifold, and it's more work to see that there is a symplectic structure on that manifold. Well, to see that there is a symplectic structure is not that hard, but to see that there is a symplectic structure for which these two are Legendrian submanifolds, it needs a little work, and this was done by Tim Perut, so we just take that particular symplectic structure. Notice that when we take this product, it secretly assumes an order among the alphas, but luckily we take this torus inside the symmetric power where the order doesn't make any difference. So at the end of the day, we have a symplectic manifold of dimension 2k, and there are two tori inside, T alpha and T beta. And now what we take is the Floer homology of this situation, well, a version of Floer homology of this situation, and I will just...
A little bit of symplectic structure, what I didn't follow.
So there is a symplectic structure, so we just pick a volume form on sigma, so it's a symplectic structure. It provides a symplectic structure on this product, but unfortunately it will descend to a singular symplectic structure on that space. And there is an argument, an analytic argument, saying that you can pick a symplectic structure on this manifold which coincides with the symplectic structure from the product away from the diagonal. So you just take that symplectic structure and then you can extend it through the diagonal. And we just take that and run the Floer machine. Well, of course, there are many versions, so we just run the simplest possible, namely, we just take the intersection points. So CF minus is generated over Z2, the field of two elements, by the intersection points of these Lagrangian submanifolds, and we define the boundary map as follows. So we only define it on a generator and then linearly extend. So this is a generator. And so we only have to specify the matrix element of the, what's the coefficient of the generator y in the boundary of x. And so the answer is that, so let me just write that down. And then I will just explain. So practically I have to explain what these symbols mean. And so one intersection is x and the other one is y. And what we do is we just take all maps from the disk in C into the symmetric power, which have the property, so this is the unit disk with I on the top and minus I in the bottom, that I goes to x, minus I goes to y, the left arc goes to T beta, the right arc goes to T alpha. The homotopy classes of such maps is denoted by pi 2xy, so we just fix a homotopy type. We count how many holomorphic maps do we have. Typically, of course, there are like infinitely many. We just take those where the Maslov index is 1, so it's a one-dimensional space. There is a reparametrization, an R action, a free R action on that, so we just factor out. So this will be a zero-dimensional manifold, and we just take the number of that, of points, mod 2, and we pose an additional constraint, namely that NW phi should be equal to 0, which means that the image of the disk, when intersected with this divisor, well, let me just write it down what this divisor is. So in other words, this k-fold symmetric power contains some submanifolds, which I will denote by green, yellow. This corresponds to those k-tuples which contain one of or prescribed w's as coordinate. And we assume that all the disks should avoid these. T alpha and T beta obviously avoid those points because the w's are in the complement of alpha and beta, and we would like to prescribe the holomorphic disks also to avoid these points. CF hat. So yeah, there is a version of that definition which gives a more sensitive invariant, but I will not talk about that today. And so the theorem of Oswald and Szabo from somewhere 2001 says that under some technical condition, which I just write what it is. So we have to assume that the diagram has a special property, what they call admissibility, but in the future, in the next 2 lectures, we will not need that because all our diagrams will be automatically admissible. So I don't specify what it is. We have that, first of all, the square of this boundary operator is 0, so we get a well-defined Floer homology theory, and HF hat sigma alpha beta W, which is just the homology of this chain complex, is an invariant of the 3-manifold Y determined by sigma alpha beta W. So how can you prove such a statement? Well, we have to prove it directly that the square of the boundary operator is 0. And to verify the second statement, one has to prove that there are these 4 moves which transform 2 Heegaard diagrams into each other, provided they represent the same 3-manifold. And for each and every move, one has to show that although the chain complex might be different, but the homology will be isomorphic. So that's the essence of this theorem. And so what I would like to do today and in the next 2 lectures is to give you a new definition of this chain complex, which will be, of course, motivated by this one, and verify this theorem. Well, verify is probably too strong of an expression, but I will sort of indicate the steps how to prove this independence.
Is this really a stable HF hat?
Yeah, so sorry, you are right. So I will define that. So the point is, yeah. This will be explained.
In the usual Lagrange homology, there is this bubbling of chromorphic disks.
Yeah, so there are no bubbles. There are no bubblings here. Practically because you have to avoid these divisors, and there is no room for bubbling. In these more general versions, you have to face the problem of possible bubblings, and then you have to see that they actually cancel. So there are boundary bubbles on the alpha and the beta tori, and they just cancel each other. But so, yeah, I just erased the definition of the boundary map. So to get a combinatorial description of the CF hat, the generators of the chain complex, this is a combinatorial object by itself. Notice that T alpha intersection T beta is the collection of those points such that xi is in alpha I and also in beta sigma I for some permutation sigma. So the generators can be described combinatorially quite easily. The problem is to determine the moduli space of holomorphic maps representing a certain Whitney disk, and to determine this number. So it was Sarkar and Wang who realized that if you assume something more about the diagram, then in fact these numbers are easy to determine. So here is the theorem of Sarkar and Wang. Let me just start with the definition. Sigma alpha beta W is nice if a component of sigma minus alpha minus beta, so these are what's called the elementary domains, so the component of the complement which does not contain any point from W is either a bigon or a rectangle. So it should look like this. It's either of this type, so this is this component we are talking about, or it looks like this. So as Peter usually phrases, they called it nice because typically these diagrams are horrible. In order to turn a diagram into nice, you have to introduce lots and lots of new intersections. You have to turn it into a mess. Nevertheless, what their theorem is that every three-manifold admits, so this is a theorem of Sarkar and Wang, admits a nice diagram, and for a nice diagram delta hat can be computed combinatorially. So, well, I will produce you another proof for this statement, and now I would like to sort of indicate why this can be true. So the whole argument So the argument for this part relies on an index theorem. So this is a theorem of Lipschitz saying the following, that so suppose that phi is a homotopy type of Whitney disks for which we have to count the number of holomorphic disks. This will give us the matrix entry of the boundary map. Then the Maslov index, or the dimension of the moduli space, can be written as the sum of the following two simple quantities, which I will now define. So this is the formula, and now I will tell you what E and P is. So this is called the Euler measure of phi, and is defined as follows. So put a point in every component, put a point di in every component di of sigma minus alpha minus beta, and let Ni to be the intersection of phi with di cross sim k minus 1 sigma. So remember, this was exactly what we previously assumed to be 0, provided di is exactly one of our wi's. But now I will put a di in every domain, and I just measure how many times phi I intersect that particular domain, and consider d phi to be the formal sum of those elementary domains by these multiplicities. Okay? So it's just the formal sum of components of sigma minus alpha minus beta. And now I will define the Euler measure of this df, provided, so E d phi is just the sum of ni E di, and all I have to define is this quantity, and where E di is just 1 minus m half if di is at 2m gone. So notice that every domain sort of has an even number of boundary paths, because the alphas and the betas are disjoint and they are the boundaries, so there is an alternating fashion on the boundary. And if I draw something and it happens to be at 2m gone, then I associate this number to it. If it has more complicated topology, then there is a way to associate a number to it, but I will not tell you what it is, and it's not important for us because in our case it will not play a role. So this is it, and then I have to tell you what p phi is, and this is called the point measure. And again, for the homotopy class, I associate this formal linear combination, and I will compute what this is. And of course, so how does this d look like, or the phi look like? So it connects x and y. So there are all these intersection points, x1, which is on alpha 1, and beta sigma 1, and of course there is a y coordinate on the same alpha 1, which is an intersection with some sigma prime 1, right? And so this is how we go from x to y. This is y1, and then we have a similar path on every alpha curve, which goes from the x coordinate to the y coordinate. That's exactly what this map does. So let's pick these points, and at xi, we just take the average of these ni's of the 4 components. So pxi of phi is just the average of the multiplicities of the 4 quadrants. So is that clear? I mean, every component of the complement of alpha and beta comes with some number ni. I just write it here. It's like 5, 5, 3, 4 or something, or 3, 3, and then I just take the average of these 4 numbers. So it's typically an integer divided by 4. I do it for every x and for every y, and I sum them up, and this is it. So this is just sum of pxi phi plus pyi phi. Okay? So
it doesn't see lots of the domains that don't have aren't.
Yeah, so this only sees those domains where the boundary turns, goes from the alpha to the beta, or vice versa.
And if there's some parts where it's like, and typically this thing is like constant at some,
then it's bad luck. Those points don't play a role here. As you know, okay. So this is an index theorem, right? It just computes the Maslov index in terms of these combinatorial data. Again, starting tomorrow, we will not need this theorem at all because we will just use it somehow. We will assume that it's true. But now, I would like to.
On the Euler measure, if you have like 3 pi over 2 corners, are you assuming that 2n naught is really like?
Yeah, so I assume that it looks like that because we will not need that. Let me just give you an argument for this. So first of all, so what is the problem with this M phi? So the first thing which I swept under the rug is that when you run this Floer theorem machine, you have to pick an almost complex structure. And typically, the boundary maps do depend on the chosen almost complex structure because we are counting holomorphic maps. And of course, the theorem states that it's sort of the homology is independent of the choice. But it might happen that sort of different maps for different homotopy types of phis, the solution space is different, but at the end of the day, they will sort of cancel out each other. The first observation is that for nice diagram, that never happens. In fact, this is a topological quantity depending only on phi, on the topology of phi. So the first lemma, so I will just erase this. If sigma alpha beta w is a nice diagram, then this number, which a priori depends on a chosen almost complex structure, is independent of the almost complex structure J. So why is that? Well, how could it happen that it's not independent of J? Well, there should be two J's, J1 and J2, for which this value is different. So proof. If not, then there are two almost complex structures and a phi such that this number is not equal to that. That would be a counterexample to the topological invariance. Okay, so what do we do if we have two almost complex structures? Well, we connect them by a path of almost complex structures, right? And we just take this moduli space of GT, where this is a path connecting J1 and J2. And we consider these moduli spaces, well, they start with finitely many points, and they end with finitely many points, but these are not equal mod 2. Well, I'm working mod 2, but it doesn't matter. We could do it over Z. The two numbers are not the same. How can this moduli space look like? Well, there are these smooth points, and then suddenly some strange thing should happen. So there should be some bubble, which means that the homotopy type of this phi should split. So this implies that phi should be written as a concatenation of two of these homotopy types of Whitney disks, each and every one of them containing holomorphic representatives, which you glue together and you get these guys which go to infinity. But the Maslov index is additive. This, of course, we only count these solution spaces if this is equal to 1. right? So what are these two numbers? Well, for a generic path of almost complex structures, the negative dimensional moduli spaces are empty. So the only way it can happen is that one of them is of dimension 1 and the other one is of dimension 0. So what did we get at the end of the day? We verified that if we have two almost complex structures for which the solution spaces are of different, contain different number of elements, then there is a Maslov index 0 domain which has a holomorphic representative. And this is a problem. Why is it a problem? Notice that in a nice diagram, EDI is either 0 if DI is a rectangle, by the very definition. It can be 1/2 if DI is a bigon. And in all other domains, we have to have a point, so this doesn't matter, because in this linear combination, the multiplicity of all the other domains, which are not bigons or rectangles, the coefficient is 0 anyhow. If DI is not bigon or rectangle, then it contains Wi, so Ni should be equal to 0. So what did we get? That the Euler measure of any domain in a nice diagram is a positive multiple of 1/2. So if M phi is not empty, then the Euler measure is some M times 1/2, where M is a non-negative number. Well, I forgot to say that, if we have a holomorphic representative, then these phi intersection DI cross sim k minus 1s are always non-negative, because we can assume that the almost complex structure makes this divisor a holomorphic submanifold. This is a holomorphic submanifold, so their intersection is never negative. So this is non-negative. And what is the point measure? Well, the point measure is just the average of multiplicities. Again, by the same principle, those are non-negative numbers. So this is some, what is a letter? F times 1/4, where F is again a non-negative integer. So far, so good? Well, now we have a contradiction, right? So how can it happen that this guy, which has a holomorphic representative, has Maslov index 0? It's a non-negative multiple of 1/2 plus a non-negative multiple of 1/4. The only way it can happen is that this number is 0 and that number is 0, which would mean that the map itself is a constant map. And of course, for a constant map, you can always decompose it, so that doesn't follow from this argument. This Gromov type argument shows that there is a non-constant map which decomposes phi. Is that okay?
Why is there no negative? Okay, so first of all, what kind of J's are you using? And
so those are almost complex structures on the symmetric power, which make these finitely many divisors holomorphic.
And why is there no negative Maslov index?
So you just take, for generic J's, there are no negative Maslov index.
So you're doing some sort of thing about bifurcation, right?
Bifurcation? Yeah, so for a one parameter family, so for a single element, there is no zero dimensional Maslov index 0 class because there is a free R action, right? So here is the set of all almost complex structures. It's a subspace where you have this assumption that these prescribed divisors become holomorphic. And for a generic choice of these elements, the 0 or negative dimensional moduli spaces are all empty. For a generic path, what you have is that the negative dimensional negative Maslov index classes will be empty, and it might pass through some 0-dimensional ones. And this is where this bifurcation happens. No? Okay, so this is the reason. This is actually the reason why we like nice diagrams, because this Euler measure cannot become negative. The point measure is always non-negative, and so when they sum up, they cannot give you 0, and in fact they can give you 1 in under only very specific circumstances. So I feel like I lost most of the audience.
In fact, positive. The point measure is in fact positive, is your point, right?
Yeah, the point measure is actually, it should be positive unless the map is constant. And that gives you the contradiction for this. And this also helps you to sort of describe what are the domains which contribute to the boundary map. And let me just give you that. So what are the phi's with mu phi equal 1? How can that happen? Well, the Euler measure is a multiple of 1/2, so there are like 3 options. It can be 0, 1/2, or 1. If it is 1, then it implies, because this is just the sum of the Euler and the point, this would imply that the point measure is 0, which we excluded. It has to be positive for being non-constant. This would imply that the point measure is 1/2, and this implies that the point measure should be 1. And then there comes a little analysis of cases, and this corresponds to the fact that the domain should be a bigone. So there are 2 points where the point measure is 1/4, and this corresponds to the case when the domain is a rectangle. They are not elementary rectangles or elementary bigones. It might happen that we have something like that. Right? In this picture there are 4 rectangles. Their Euler measures are all 0, and there is 1 bigone. The Euler measure is 1/2. So if you sum them up, you have exactly Euler measure 1/2. The point measure can be taken only in these 2 points, where it's 1/4, 1/4, and they will add up to that. And the same remark applies here. So you have this diagram, and you only have to count the embedded bigones and rectangles. Well, you need an argument why these are embedded, and this is what Sarkar and Wang did. And so this gives us the motivation for giving the combinatorial description, as I will do next time. But
I'm a little bit confused about this. So where does this analysis go? Is this analysis goes on this symmetric product?
Yes.
Or on the Riemann surface?
No, the symmetric product.
So how does this disk, the symmetric product, is related to this two-gun and four-gun and surface?
So every map, if you take a map which goes into here, it immediately gives you a formal linear, so this is U representing phi. So phi is a homotopy class of such maps. Once you have such a gadget, then it gives you a formal linear combination by computing these intersection numbers. So a map into the symmetric power gives you a formal linear combination of domains on the surface. And somehow this is where you want to do the combinatorics, and this is where you don't want to do the analysis, but you have to. And so this construction just brings you down from the symmetric power to the surface. This is what you were asking? Okay. So this is the...
Di is a domain in this surface.
Yeah, di is just, you know...
So that can become polygons and this, rectangles.
Exactly.
And many other things, right?
Yeah, so typically, of course, they are not simply connected, but you know, this is like a Heegaard diagram: 3 blue, 3 red, and the di. Well, of course, I will not be able to pinpoint one, but it's something like that, a connected component. Right? You see? Oops, no, only up to here. And this is, for example, not simply connected. It looks like that. A nice diagram requires you to put a base point there. Typically, if you draw a diagram, it's not nice. I mean, it's nice in some sense, but it's not nice in the technical sense. And the theorem of Sarkar and Wang actually showed that somebody gives you whatever diagram he likes, and you just use isotopes and handle slides, and you turn it into a horribly complicated nice diagram. Instead, I would like to give you another way of producing a nice diagram based on a theorem, obviously, but I will just give you the construction.
So the n sub i's then are computed by intersection numbers with those di cross sim inverse.
Of course it has, so, you know, somehow, yeah, let's stick to that. So this is what I wanted to tell you about this. This will motivate our choice of the chain complex on Thursday or Friday or whenever. But I would like to convince you that actually these nice diagrams are not that rare. One can easily come up with a nice diagram, but before doing that, let me just point out one thing. So you remember this Heegaard decomposition of what I was showing to you as the first example. And we had to put down the W's. You remember that, right? Okay, so first of all, a remark. This is a Heegaard decomposition of S3. Well, it's a genus 1 Heegaard surface, so this 3-manifold admits a genus 1 decomposition. It can be only a length space, and because this alpha and the beta intersect each other in one point, it's not very hard to show that it's S3. Remember, we identified this with that. Notice that it's a nice diagram because there are no other domains. We only have rectangles. It's actually a very special nice diagram. We only have rectangles. And there is a trick. So what happens if I, instead of putting one point in each row and each column, so I put down in some, let me just do one more. Okay, so I put down the W's in some way. For example, like this. What happened? I can do this with the W's, and I can produce another set of W's, which I will call O's, which obey the same rule. In every column and in every row, there is one O and one W. Well, this is not necessary to turn something into a multi-pointed Heegaard diagram, but it gives me something else. Namely, it describes a knot. So W and O provides a knot, or sometimes a link, in S3. Namely, the convention is that we just join the vertical things, and then we join the horizontal ones, and when there is a conflict, which one goes over and which one under, then always the vertical goes over. like this. So in this way we produce a link or a knot in S3, and the fact is that every link can be produced in this way. So a grid, i.e. an n by n diagram with n w's and n o's produces a link, and conversely every link can be given like this. Obviously, what's the special thing about this link? It has only horizontal or vertical arcs in the projection, plus there is no such crossing. Right? This is forbidden. And I claim that every link projection can be arranged to have these properties. For example, if there is a skew arc in the projection, then you just introduce these little steps. And the effect will be the same. And if there is such a crossing, then you apply the swastika. Right? Then you turn it into like this. You see, I just rotated a little bit. So every projection can be turned into some. So suppose that, or 3-manifold Y is a double-branched cover, which means that there is a map F which is typically 2-to-1, except along a knot it's a 1-to-1 map. So it's 2-to-1, except along L in S3, a link, it is 1-to-1. Suppose that such a map exists, then what we do, we take this link, we put into a Heegaard decomposition like that, with O's and X's, with O's and W's. So put L into a grid. So we have, or Y here, this is S3, and inside S3 we have this torus with plenty of red curves and plenty of blue. And the suggestion is that pull this back, pull this Heegaard decomposition back. So take the inverse image. This is sigma will be F inverse of the torus, and consider the pullbacks of the alphas and the betas. The first thing, which is not very hard to check, is that this will be a Heegaard decomposition upstairs. So the pullback will be a Heegaard diagram for Y, but there is a little problem with it, and the problem is that it's not nice at the moment. Why is it not nice? Because let's see what happens with a component. So here is an alpha component downstairs. It has 2 points, one O and one W. What happens when we take this cover? Well, the cover is 2-to-1 along each point, except when we have the point where the knot goes through the torus, it's a 1-to-1. So over these domains, we just have 2 disjoint components, 2 rectangles, which is fine. In a nice diagram, we can have as many rectangles as we wish. But unfortunately, from this, upstairs, we will create an octagon. So in one component, we will have 2 octagons. But remember, the rule is that in one component of sigma minus alpha, you are allowed to put down 1 point. On the other hand, we would like to put a point in every domain which is not a bigon or an octagon or a rectangle. And we have 2 octagons. So what we do, we introduce some more curves, And the idea is very simple. We just take this curve and we just consider its pullback, which upstairs does the following. So the inverse image looked like this. It was a 4-punctured sphere. The double branched cover of an annulus branched in 2 points is just a 4-punctured sphere which contains 2 octagons. Well, I'm not that good in drawing octagons. And another one. And now this new circle will just separate these 2 octagons from each other, and now we are allowed to put 2 base points, one each, because the one sigma minus alpha component now falls into 2. So in this way we can create a Heegaard diagram gives sigma alpha beta w such that alpha and beta are pair of Pence decompositions of sigma, and all components of sigma minus alpha minus beta are rectangles or octagons, and these contain base points.
I guess you have to draw a new beta curve as well.
Yeah, so you have to do it in every slice, and then you have to do it in every beta, in every row. The problem is that not every 3-manifold is a double-branched cover of S3, but every 3-manifold is a simple triple-branched cover of S3, and you just have to modify this algorithm a tiny bit to give the same kind of decomposition. And so nice diagrams are pretty flexible. By the theorem of Sarkar and Wang, every diagram can be isotope to be nice. These diagrams are very rigid because they come from a very strict consideration, and what we'll do tomorrow, I will define a new class of Heegaard diagrams which are sort of in between the two. They will be nice but not as rigid as these ones, and those will be the diagrams we will use to prove the theorem of Peter and Zoltan in the combinatorial setting. I should mention that this is a joint project with Peter and Zoltan. So, okay, so that's it.